Morning, everyone. I have a few slides here on plant water relations. It'll cover some of the same material in the book, but hopefully kind of expand on it and highlight some of the important parts. I'll do this in a series of videos, try to keep them about 15 minutes, and I will post a quiz. I don't know actually if I'm going to post a quiz this week. I haven't decided. Maybe we'll do some other assignment instead of a quiz. So we'll see. Keep an eye on Canvas. Before I get started, I just wanted to give credit where credit was due. My first plant ecophysiology, actually that's not true, my second plant ecophysiology teacher and PhD advisor, Dr. Barb Bond, who was at Oregon State at the time, she made a lot of these slides. She's like a plant water relations expert. And so I took those slides and modified them and just wanted to make sure I gave credit to her. She has since retired and I think opened a vineyard with her husband. So I think she's enjoying retirement a lot. All right, let's talk about how plants are how water is moving through plants. So water is being pulled up through the plants, not pumped up from the bottom. And so when we think about the movement of plants, it's good to think about it from starting at the leaf and then working our way down, which is a little bit opposite since the source of the water in the plants is coming in the soil. But since that's where the force and the tension is generated, we'll kind of start in the leaf and then work our way back down. So water within the plant forms a continuous network. So that water that's moving up through the plant, it's all connected. All right, so it's a continuous network of water, and so we often refer to it as the water column. And it begins with that film of water that is surrounding the soil particles. So if you look in the bottom kind of image down here, oh wait, let's see, I can draw now. I just paid for the updated subscription. Oh geez, I don't know how to draw yet. Oops, not like that. All right, I'll have to work on that, but there is a way I can draw. Anyway, this lower picture, you can see these soil particles out here with the water around them. That's where this continuous column begins. And from there all the way up into the leaf where the liquid converts to vapor, that is all a continuous column of water. So we refer to this continuous kind of continuous column of water as the soil plant atmospheric continuum, or the SPAC. So you'll see the SPAC referenced sometimes. You'll hear it. It's a kind of a cool acronym, but we actually don't use it as much as we should. So maybe some T-shirts or a sticker are in order with SPAC on it. So if anybody has any good ideas on cool SPAC stickers or T-shirt logos, let me know. Okay. So this just kind of represents the water potential of different tissues and how the water is moving up through the tissues. And I kind of mentioned this in the other video on measuring water potential, and it talks about it in the book, but water potential is the measure of potential energy of water. And like all molecules, they move from places of kind of high pressure to low pressure. And so values that are close to zero are relatively high, and values that are really negative are relatively low. And so that's why water is going to move from the soil. So you can see here a kind of realistic value of watered soils is minus 0.1 megapascal. And then the atmosphere is somewhere in the ballpark of a minus 100 megapascals. So really dry compared to the soil and any plant tissue. So that water potential is much lower. And that, again, is the driving gradient to move this water up through the plant. So I explained this in the water potential video, but I guess I'll say it again. The potential energy of water is, it's all relative to standard or pure water at standard temperature and pressure. So basically, 0 is pure water that's at 20 degrees Celsius at atmospheric pressure at sea level. That's what 0 is. So anytime you eliminate or remove some potential energy, your values are going to be negative. If you add potential energy, your values are going to be positive. And so we'll talk about what things are positive and negative in just a second, and hopefully that'll help that make sense. So this is just general idea of SPAC. Let's talk about the water potential and what goes into the water potential here. So water potential gradients in trees under static conditions is what we're going to talk about first. That's when so hydrostatic conditions means that the water potentials within the plant are uniform, and so that there's no movement of water. So we would think of this happening at night. And this is an equation to estimate water potential, and just really tells us what factors go into estimating or contributing to water potential. The subscripts might be a little different from the book. There's really no great consistent way of indicating these things, so I apologize. All right, so if we're thinking about water potential, and in this case, we're going to think about it at a particular place, not necessarily in the tissue, but at a particular kind of place on the tree, if you would. There's 4 main factors that contribute to that water potential. The first is solute potential. That's how many sugars or other solutes are in the water. Pressure potential is well, let's go down. As we go through each of these, I'll kind of like highlight its definition down here, and then also talk about whether it's positive or negative. So solute potential is generally negative, and what that means is if you add solutes, I'm doing a table shaker right now. That's a universal sign for adding solutes. So if you were to add solutes to the water, it's going to reduce the potential energy. It's starting to interact with those molecules and reduce that motion and that movement, and that reduces the potential energy. So that's typically going to be a negative impact on water potential. Pressure potential is actually positive. And I think the easiest way to think about this is a water balloon. If you fill a water balloon up with water, as it gets fuller and fuller, it's expanding. And so that water is pushing out on the wall, or the water balloon, or the balloon itself. But that balloon is elastic, and it's pushing back in on the water contents. That's pressure potential. So in a plant, it's those living cells. When they get full of water, the cell walls are creating pressure back on the contents of the cell, and that is pressure potential. Okay? It's only happening in living cells. In the xylem cells, which are dead, we don't have pressure potential, or it tends to be 0. The third one is matrix potential. Matrix potential is the physical potential. So, I was going to have a picture of this. We'll see one in a little bit, but for now I'm going to try to do it with my hands. So the easiest way for me to think about this, at least right now, is in the soil, because this is what drives water potential in the soil. So let's say you've got some soil particles, and you've got this little space. Okay, my hand is supposed to be the space between particles. You got a particle up here, you got a particle here, here, and here. And if there's a little water in this little space right here, there's a little meniscus right there. And that water is held in place due to the physical forces of this little pore space in the soil. All right, so it's really kind of water being held in pores. So you can also think about it like a piece of cloth. If you put it in water and pull it out, a lot of the water drains out, but some of it's going to stay in those little pores in the material, and that's held there due to matrix potential. So the smaller the pore, the tighter it holds onto the water, and the more negative the matrix potential. All right, and that's again generally a negative force. So it reduces the potential of energy of water because it's held there by those physical forces. And then the last water potential is the gravitational potential. And this is due to just gravity and where the water is in a tree. So the higher it is, the more potential energy it has, because if it were to fall, it would have a lot of energy as it falls back or is pulled back to Earth's surface due to gravity. All right, so that's a positive force. So in really tall trees, that gravitational water potential can be really important. For herbaceous plants, we generally just ignore it. But we'll look at a slide. Actually, it's on the next slide. Let's look at that. All right, so those are the 4 major factors that contribute to water potential. The 2 we're going to talk most about are solute potential and pressure potential. Within a plant, when we talk about soil, matrix potential will be a lot more important. And if we're talking about tall trees, gravitational potential will be important. So Barb, who again these slides came from, she worked on tall trees. She was really interested in why do the old growth forests in the Pacific Northwest slow down their growth. And so some of that had to do with the fact that these tall trees were dealing with this gravitational water potential. So she thought about this a lot. I am now working on grasses and forbs primarily, or shrubs, and so I tend to ignore it. So it just kind of depends on what kind of species you're working on or what system. All right, so here's just an example of a tree. And again, this is under hydrostatic potential gradient, meaning there's no water movement. So we're going to imagine that the soil is at minus 0.1 megapascal. And again, there's no water moving in this 30-meter tall tree. So if we look at what the water potential is in different tissues, this is kind of what we would imagine. So gravitational water potential increases at 0.01 megapascal per meter. So megapascal are the standard units we use for water potential. And so that increases for every meter. So at a 30-meter tall tree, the gravitational water potential is plus 0.3 megapascals. Remember, that's gravitational potential is going to be positive values. At 20 meters, it's 0.2, and at 10 meters, it's 0.1. Well, if this, so the leaf water potential then is minus 1 megapascal. So if we combine these in the equation, and I should say this leaf water potential value incorporates, I'm going to go back a slide for a second, it incorporates solute potential, pressure potential, and matrix potential. All right, so that's those three factors are in here, and we're pulling out the gravitational potential. And you can see if we add these together, that equals minus 0.1 megapascal, which is the same value as soil. If you move up, gravitational potential is plus 0.2, and so in order to end up with a minus 0.1 megapascal water potential, leaf water potential has to be minus 0.3. And if you look at the top of tall trees, the water potential in the leaf water potential has to be minus 0.4 to kind of offset the gravitational potential of 0.3, ending up again with minus 0.1 water potential. So we have a minus 0.1 water potential of the water throughout the entire water column in a tree. And in that case, there's going to be no movement of water. There's no water potential gradient. All right. But this helps you kind of see kind of the effect of gravity on what the water potential of the plant tissue has to be. Notice that the gravitational water potential is not included in the water potential we calculate of individual cells or individual tissues, but rather the water potential in those tissues has to compensate for gravitational water potential. So let's go back a slide. Notice that if we were to measure the water potential of the leaf or the stem, it is going to vary throughout the plant. So it's going to get more negative even when there's no water movement because it's compensating for the gravitational water potential, right? This also points out the fact that in tall trees and really any plant, the water potential is going to be more negative at the tip than it is the base. Now in really short plants, it's so small that we really can't measure it with the equipment we have, but it is occurring at all times. Okay, try to get through this here. I'm trying to keep them 15 minutes. So that's under hydrostatic conditions. During the day, when a plant is actually transpiring, the pressure potential gradient is going to be greater than the hydrostatic gradient. So that means there's going to be a more negative value at the top of the tree pulling water up the tree, and that's going to result in the movement of water. So here's just an example of what this tree might look like during the daytime. So again, water at the soil is minus 0.1. And then we still have that gravitational potential to think about. But if we look at the leaf water potential, it's now minus 0.8 in the leaves, or in the leaves of the upper canopy, minus 0.6 of the leaves in the lower canopy, and the stem is around minus 0.4. So then if we add the gravitational and the leaf water potential together, you can see we do have a water potential gradient up the tree. at the tip or at the top, it's more negative than at the bottom, and so we know we have water moving up through that tree. And so that's how the movement of water through the tree is generated and gets going and moves down that water potential gradient. The one thing I want to say, I've got a slide later that I'm going to talk about it. I forget where, but I feel like I'm kind of like poking around this issue, so I'm just going to talk about it right now. So this is this hydrostatic gradient when water's not moving. This is what we would assume is happening at night, right? Sun goes away, stomates close, there's no water movement through the plant. So this you can utilize this in one way, which is really effective, in that if we assume these plants aren't transpiring, what happens at night is that we get this hydrostatic gradient where there's no movement of water. And essentially what's happening is the leaf water potential is equilibrating with the soil water potential. And so as long as you account for gravitational water potential, you can measure leaf water potential and know what the soil water potential is where the roots are. All right, which is really important because it's hard to know where the plant is getting its water. All right, rooting depth is a really hard thing to measure. And so this is one way of actually seeing what's the water potential of the soil where this plant's roots are located. All right, and you can do that if you measure them at night. We call them pre-dawns. You go out before the sun rises, you measure water potential, and it tells you something about the soil water potential. Now, there's one caveat to this, is this technique was developed when we made the assumption that there was no transpiration at night. We now know in the last really kind of 5-6 years, this area of research has kind of exploded. We know a lot of plants are transpiring at night. Some of them are transpiring a lot. There's a recent paper by Kim, oh gosh, I'm blanking on her last name right now. I'll think about it and tell you later. But she did this on grasses in the tallgrass prairie, and some of them, like 10-15% of their entire water budget blows out the leaves at night. And so there's a large amount of water coming out. If that's the case, then you can't measure the leaves at night and estimate soil water potential because those leaves are never equilibrating with the soil. So it's a potentially cool thing. There's also some potential problems with it using that method, but I just bring that up now. Okay, sorry, I went over the 15-minute mark. We're at 17:40. I'm going to turn it off, and then I'll make another video kind of thinking a little more about the gaseous phase of water transport and then estimating transpiration.